This is the first lesson on Chapter 3, which goes into more detail about one of the elements that are really important in living things, carbon. We're going to start this lesson by watching a short video on YouTube. And while you're watching, I want you to look for evidence why carbon is so versatile.
Just about everything that and in this world is made at least partially of carbon. Carbon is crucial in forming the bonds that make up living things and the stuff that certain living things like to make.
Carbon is the most abundant element in the universe that forms solid structures. Of course, hydrogen and oxygen and helium are more abundant. Carbon forms structures. As a matter of fact, it's a very unique element. It's an enchanted element.
The key lies in the configuration and size of the carbon atom.
What makes carbon so versatile is two things. Number one, the amount of electrons that it has in its outermost shell, which we refer to as the valence shell, is 4. And it's also in the first row of the periodic table, which makes it a very small atom.
The carbon atom's 4 valence electrons bond with larger elements, such as metals, as they give up electrons, and smaller elements, such as gases, as they try to gain electrons. As a result, carbon forms an amazingly broad range of compounds.
In fact, today there are probably over 10 million known carbon compounds.
The most stable carbon-to-carbon bond is found in diamond, a crystalline lattice of pure carbon.
Diamonds have extreme hardness because the carbons that exist within diamond have been compressed under extreme pressure over billions of years to form this interlocking network of tetrahedra. And this interlocking network of bonds between carbons makes this extremely, extremely hard material. In fact, the hardest naturally occurring material known to man.
Carbon, with its unique bonding capabilities, is also the key element of living things. Thus the phrase, carbon-based life forms.
Carbon is an ideal chemical element to be just stable enough to make the stuff of life and the chemicals with which life does business, but just unstable enough that it doesn't cost too much energy to get that chemistry going.
It's this ideal combination of stability and reactivity makes carbon the backbone of all living systems. With carbon providing the critical bonds, simple sugars become complex molecules like DNA. It's truly the element of life.
How to get the most of Grammarly Free.
It's Kayla on behalf of
Okay, so through that video, I asked you to watch out for evidence of what makes carbon so versatile. So what did you come up with? Hopefully you noticed that carbon has 4 valence electrons, and also it's a relatively small atom. Those two properties allow it to do the third thing, which is to form many different compounds. So for moving forward, we're now going to be kind of looking at different examples of carbon compounds to appreciate the diversity of carbon and also talk about its importance in living things. As mentioned in the video, carbon is the backbone of biological molecules. All living things are made of cells, but within those cells are organic compounds, including the 4 that are listed in the red box here: carbohydrates, lipids, nucleic acids, and proteins. These are the large biological molecules that we're going to be studying in more detail in this chapter. Another term that's used to recognize carbon compounds is organic compounds, or perhaps you've heard of a class or a study called organic chemistry. So this specifically is looking at organic carbon-based compounds. And so now we're going to start seeing some examples of organic compounds ranging from very simple, the simplest one actually shown there at the bottom left, methane, to very complex like cholesterol shown at the bottom right. Something they both have in common that many organic compounds do is that they're mostly comprised of carbon and hydrogen atoms. But sometimes you'll see carbon bonded to other elements like hydrogen, oxygen, nitrogen, sulfur, and phosphorus. When forming these bonds with other atoms of other elements, or even with carbon, different atoms of carbon as well, carbon can form many diverse molecules because of the way that it bonds with those other atoms. When carbon forms 4 stable covalent bonds at the same time, it's referred to as being tetravalent or having tetravalence. So one example of that is shown here as well. The molecular structure for methane, CH4, shows how the carbon is sharing electrons with 4 hydrogen. And each of those is a covalent bond. So remember that covalent bonds are formed due to the sharing of electrons. And so just as a little review from last chapter, if you look at the structure of carbon, it has 4 valence electrons. It can have 4 more. So the way that it can get those is by sharing them, one with each hydrogen. Now then, hydrogen would have 2 valence electrons through that sharing, and the carbon, after it's fully sharing with 4 hydrogens, would have a total of 8 valence electrons. So tetravalence does not just occur in methane. These are also examples where carbon is sharing electrons with 4 different atoms. It could be carbon or it could be some other element. These are different ways to show molecular structures. Whenever you see where cortisol shows and there's these hexagons, sometimes they don't write hydrogens, you just assume that they're there, and carbons would be at the intersection of the lines. But again, this is not chemistry class, so I just wanted to show you some different examples of carbon compounds so you can have a better appreciation of how complex that category is, how diverse they are. And we'll look more at these examples when we talk about the specific types of large biological molecules, carbohydrates, lipids, proteins, and nucleic acids. Sometimes carbon does not bond with 4 other atoms. In fact, shown here is carbon dioxide, which it's only bonding with 2 oxygen atoms, and it's sharing 2 pairs of electrons between the carbons and the oxygens. So these are double bonds. Another example of how diverse organic molecules can be. Carbon also has the ability to link together with many other carbons, forming long chains. Propane is an example of a hydrocarbon. It's a molecule composed only of hydrogen and carbon. All of these are hydrocarbons because they're solely composed of carbons and hydrogens. We'll see hydrocarbons again in a later lesson when we are talking about lipids. The hydrocarbon tails that are part of lipids or fats are have a property of being nonpolar and hydrophobic, which plays a role in how they're able to store fat, which is a long-term storage of energy resource in an organism. And also, we're utilizing petroleum for fossil fuel purposes because of all of the energy that's stored within those hydrocarbon bonds that, when released, can be used as a source of energy. So that's a little preview into one of the topics that we'll dive into deeper when we get specifically into the category of lipids. But that concludes the first part of chapter 3, an introduction to organic chemistry.